Greetings. Let us continue with the discussion on numerical number 4. The statement of numerical is such: determine the depth at which a circular footing of 2 meter diameter to be founded to provide a factor of safety of 3 if it has to carry a load of 1800 kilonewton. The foundation soil has shear strength equals to 12 kilonewton per meter square, phi equals to 30 degree, and unit weight of soil is 17.8 kilonewton per meter cube. Use Terazaghi analysis. In this numerical, he demands to find out the depth at which foundation has to be founded so that it is capable to take a load of 1800 kilonewton against a factor of safety given to us 3. The various soil parameters has been given, like shear strength is given to us 12 kilonewton per meter square, angle of repose is given to us 30 degree, and unit weight of the soil is provided. Also, he says that use Terazaghi analysis, but he doesn't specify any failure mode of the soil. In that case, we are going with the general shear failure criteria. So based on general shear failure criteria and angle of repose, we can find out the bearing coefficients like NC equals to 37.2, NQ is equals to 22.5, N gamma is equals to 19.7. With the reference to the empirical formula suggested by Terazaghi for circular column, QS is equals to 1 upon F in bracket 1.3 CNC plus gamma into D in bracket NQ minus 1 bracket close RW1 plus 0.3 gamma B n gamma RW2 plus gamma D. This gamma D is nothing but the surcharge load. Here RW and RW1 and RW2 represents the factors related to the water table, but here the water table concern is not mentioned. That's why we'll consider as a default value as a 1, where the D is the depth of the foundation, which is unknown to us, and B is the width, which is given to us about 2 meter. In case of a circular column, we consider B equals to the diameter of the column. Intentionally I have not removed this B because we have a general practice to represent width as a B, and we are having general practice of representing the depth of foundation as D. If I put here D here itself, so it will get confused. That's why I have mentioned it as a B, and later on I will substitute instead of this B the diameter of the footing. After substituting the respective values, we have the resultant as 1 upon 3 in bracket 1.3 multiplied by 12 the shear strength parameter, shear strength given to us, multiplied by 37.2 the NC value which we have got from the table with reference to phi 30 degree, 17.8 into D is the unknown depth of the foundation which we are interested to find out here, and in bracket NQ the coefficient related to the shear 22.5 minus 1 plus 0.3 gamma value is given to us 17.8 multiplied by the width of the foundation is equals to diameter of the foundation which equals to 2 multiplied by the n gamma value which is 19.7, and plus in addition to this we are going to apply the surcharge 17.8 multiplied by the depth at which foundation is being raised, but depth is not known to be put in terms of unknown parameter D. So I get a relation QS is equals to 263.57 plus 145.37. Let us say this is the equation A, which is related to the capacity of the soil. Now let us see what the demand is imposed on it. The demand imposed is the applied load divided by area which is provided for the foundation. In the case of circular column, this will be pi by 4 into 2 square, because 2 is the diameter of the column given to us. So 1800 divided by pi by 4 into 2 square, it comes to be 572.95. The shear which is applied on the the stress which is applied on the foundation is about 572.95. Then we let us say this is equation number B. Now I equate that the load which is coming from the column, the stress which is demanded by the column should be equal to the stress which is applied on the foundation. Based on this equilibrium, let us say we are equating the equation A and B. So from this relation we get 572.95 equals to 263.57 plus 145.37. It's a linear relationship. After solving this equation, we get the depth requirement is about 2.13, say 2.15. Now in this case I will not go for the design of the depth, because in case of foundation engineering, depth requirement is not being concerned. We are only concerned about what proportion we require. So here D is nothing but the small capital D is nothing but the depth of the foundation, not the not we can say it is a diameter of the footing. Okay, now let's move towards the next case of the your shallow foundation. The next case is about the combined footing. When we are going to adopt a combined footing, when the footing is going to support two or more column in a row, and they are being provided in circumstances where the foundations of the columns are overlap, the that is the distance between the column is very much less. In that case, we are going to provide combined footing. When the safe bearing capacity of the soil is too low, in that case also we are going to provide the combined footing. When the exterior column is near about the property line, in that case we are also going to provide combined footing. When two columns are being supported and they are nearer to each other, the footing overlaps, then we are going to provide a combined footing for that. But in some cases, what will happen, this column may have unequal loads. Due to this, the requirement of the area will be different. The area requirement is different. In that case, what we have to do, we have to go for averaging of this area. In that case, we are going to refer the shape as a trapezoidal shape. The small area requirement will be provided for the light loaded column, and large area requirement will be provided for the heavily loaded column, and thereby we, for an economy, will give a sloping edges to it, so that the material saving is there, as well as there the requirement of area will get mitigated. But this type of foundation is adopted only when the unequal loads are applied on the two columns which are supported by a single foundation. The second case is the strap footing. In this case, the column is exactly at the building line. If the building line is a building line and the property next to that is of a government property, then we can have the enlargement of the foundation towards his property. But it is being a private owner, he will not allow us. Okay, in that case, what we have to do, we have to place the column at the edge, and we have to enlarge the footing in a in the opposite direction along the our property line. That's why it will be appearing like a eccentric column. So in this case, the eccentric moments will get attracted by the foundation. To balance it, this foundation will be anchored with a nearby nearby column which is axially loaded, or which is having very much less eccentricity, thereby ensuring that the load is going to be taken in a dual action. Okay, the connection which has been provided with this two footing is with the help of a rectangular beam, which is just placed above the foundation to connect the two columns. Its job is to connect this column and transfer the loads from eccentric column to the axially loaded column. But there are there are two footings going to act unitedly. That's why we can term it as a in the head of a combined footing, and we are going to use a anchor beam for this. That's why the name is given as a strap footing. Let's go towards the design assumption for the combined footing. In case of combined footing, what we are going to assume, the very first assumption is that the footing or mat is infinitely rigid, and therefore the deflection of the footing or mat does not influence the pressure distribution. What we are going to assume, that the footing is said to be a very rigid element. Any deflection below the soil, or the any settlements below the soil, is having a negligible effect, and the pressure distribution along the footing is uniform. Okay, the next one, the soil pressure is distributed in a straight line or a plane surface, such that the centroid of the soil pressure coincide with the line of action of the resultant force of all loads acting on the foundation. Means what, when we are going to assemble two columns, the two columns may have equal load, or the two columns may have unequal load. If they are going to have unequal load, what will happen? There will be a loading centroid, or a loading CG generated. This loading CG should be balanced with the area distributed of the footing CG. That's thereby ensuring that there is no extra overturn, or no extra overturning moment acting on the footing. Okay, let's see in detail with reference to design of a combined footing. Let us say we have an assembly here of two columns C1 and C2. They are being loaded with a load P1 and P2. P1 and P2, and let us say the P1 and P2 are now being equal in magnitude. Hence, we may go for a rectangular shape of a footing. Let B be the width of the footing and L be the length of the footing. Hence, the total load on the footing will be equals to P1, the load coming from the column 1, and plus the P2, the load coming from the column 2, plus I will add some weight with reference to the weight of the footing, self weight of the footing. Let us consider this is in a range 10 to 20% of the total load applied on the footing, that is addition of P1 plus P2. So that's why I will write here 10 to 20% total load of the total load P1 plus P2 as a self weight. Now then, what is our interest here? Our interest is here to find out what is the cross section requirement for this type of footing. For that case, what we'll do, then the area of footing can be worked out as the total load divided by shape bearing pressure. This shape bearing pressure can be estimated with the help of the empirical formulation or soil parameters given to us. The empirical formulation which has been suggested by Terazaghi and many more scientists, we can use that one, and we can put that safe value here, shape bearing pressure value here. The load divided by safe bearing pressure will give the resultant as a area requirement for the footing. Now what is our job? We have to validate both the assumption. The very first assumption is that the pressure is uniformly distributed, and second assumption is there is no overturning moment caused by the by the applied loads. Now since the applied loads are at a certain distances, now to obtain this, to validate these two assumptions, let us know how the centroid of the loading and centroid of the your footing is going to act. So in this case, what we will assume, the centroid of the load and the centroid with reference to area should match. Now to obtain the length to obtain the length centroid equate centroid due to the area with the centroid due to the loading, because what we have considered here, the pressure is distributed along the length of the footing, and on the contrary transfer direction, there is a distribution of that forces. Okay, the total we will consider that the footing is going to act as a rectangular beam of length L and width B. Okay, and depth D of that will be below the depth of the foundation. If you see the cross section, so here depth and L will be subjected to the application of the forces, statics of the forces. So based on that, the geometric centroid x bar will be worked out as L by 2, and the loading centroid will be found as a x bar is equals to P2 into L divided by P1 plus P2. What is the meaning of this? I am going to take a moment of the loads along one of the columns. So I am considering the column, the moment of the load along the column C1, the P1, and there will be no eccentricity since I am going to taking the moment along the P1 itself. That's why P1, P2 into L will the moment divided by the total resultant force P1 plus P2 into x bar. From that relation we get x bar is equals to P2 L divided by P1 plus P2 plus A. What is A here is a projection of the first column with reference to edge column with reference to the edges of the footing. If we come towards this figure, we see that the column P1 is at a certain distance from the edge of the footing. Let us say this projection is A. If I want to go up to centroid of the loading, what I have to do? I have calculated the centroid with reference to P1. I have to add this small projection to it. So it will be x bar is equal to P2 into L divided by P1 plus P2 plus A. A is the projection which I have added here. Now what I will do, I will equate these two and I will get a relation L equals to 2 in bracket P2L divided by P1 plus P2 plus A. Now with once I have got length, the second part of the contradict part is the width we have to find. The width of the footing can be find out AF divided by L. Since we are going to assume that the footing is a rectangular footing, that's why the width can be estimated by the simple relation AF by L. Now based on the obtained dimension, we can select a suitable dimension for a footing. The obtained dimension may be in a fraction part, we can round up it and we have to select one of these one. Now for the check, we will assume that net upward pressure, we will calculate the net upward pressure for the footing, that is Q naught, which equals to total load divided by area provided. This Q naught upward intensity should be always less than the applied intensity, applied stresses on the footing. If it is so, then we are going to say our footing is a stable one. So footing will act as a beam subjected to an upward pressure distributed over the entire length and the two concentrated load from the columns downward. Now if we want to go towards the statics, how the things is going to happen, what amount of shear force it is going to carried by the footing, what amount of the moment is going to carried by the footing, then we have to discuss about the failure modes of the footing under the applied load statics. Okay, loading statics. For that we'll have a long discussion in next session. Till then, goodbye, be safe.